Today, we are going to explore a conflict between the macroscopic and microscopic descriptions of electromagnetic radiation, that is, light. And we'll explore that contradiction in the quantitative context of a three-dimensional radiation cavity. Cool, right? Let's get started. Last time we explored the parameter h, Planck's constant, which set the scale for quantum effects. It was, as we interpreted it, the parameter that sets a finite resolution on the information carrying capacity of space and time. Because h is kind of a wonky number, we multiply it by another wonky number, the speed of light, c, which sets the speed limit, if you like, for how fast information can travel through space and time. Multiplied together, hc gave us a number, 1240 electron volt nanometers, that we were able to use to interrogate when quantum effects become important.
We'll explore both of these ideas today explicitly in terms of light. Light is rarely monochromatic. The colors we see outdoors all originate from sunlight. Walk by a tree and observe the green leaves. The chlorophyll in the leaves absorb much of the red and blue light from the sun, reflecting back all the rest. From our perspective, what remains yields different shades of green depending upon the chemical details of the individual trees and their leaves. Nevertheless, we can split the colors of sunlight using a dispersive media such as glass or water, that is, some kind of prism. A prism causes light to refract or bend differently depending upon its wavelength. Typically, bluer light bends more than red light, separating the sun's rays into a rainbow. Water droplets in the atmosphere sometimes give us the eponymous example of a rainbow.
Light is known to be comprised of waves in the electromagnetic field, or more appropriately, waves in the electromagnetic field are what light is. While it is true that electric and magnetic fields are often sourced by charged particles and moving charged particles respectively, light does not need any kind of electric charge to exist on its own. Indeed, the wave nature of light, the dynamic nature of these waves, allow electric fields to source magnetic fields, which in turn source electric fields, which in turn source magnetic fields. And in fact, this pattern allows us to see an oscillation in the electric field, which coincides with a similar orthogonal oscillation in the magnetic field. That is to say, a light wave.
The individual colors of light correspond to specific wavelengths of those field oscillations. Alternatively, we can assign colors to specific frequencies of the light. As with any wave, we have a simple relationship between the speed, the wavelength, and the frequency. That is, the speed of light is equal to its wavelength times its frequency. Classically, the amplitude of the electromagnetic wave, say A, scales with energy. So more precisely, E scales with A squared. For an electric lamp with a dimmer switch, you can lower the energy of the light emitted by reducing the electricity flowing to the bulb.
We've said it a bunch. Quantum mechanics imposes a finite resolution on the information carrying capacity of space and time. For the electromagnetic field, this finite resolution amounts to a finite resolution on the energies of the electromagnetic field. So in particular, light waves, are built up of tiny little packets, discrete packets, of a predictable amount of energy. Put differently, it costs a small but finite amount of energy to create a disturbance in the electromagnetic field. Moreover, the cost of that disturbance depends upon the wavelength of the light that you're looking to create. The higher the frequency of the light, the higher the cost energetically. More precisely, quantum mechanics tells us that the energy of the smallest possible excitation of the electromagnetic field at a wavelength lambda is given by hc over lambda. That's right, our familiar constant hc, 1240 electron volt nanometers.
Or we can use the relationship between the frequency and the wavelength of light to rewrite the energy of a photon as E equals hf.
The quantization of light into photons was a crucial breakthrough in our understanding of how quantum mechanics works. This quantization of light energy, these photons, was not immediately obvious to physicists at the turn of the 20th century. And the fact that these quantized units of energy also depend upon the wavelength itself, the fact that light costs more if it has a higher frequency to produce, was not at all obvious. This idea of photons helped resolve a major problem in our understanding of the electromagnetic field, as we now discuss. You might recall from elementary physics that electric fields vanish on the surface of a conductor, that is to say, on a surface of metal. Why might this be? Well, remember that metals have a bunch of electrons and other charged particles, whatever, floating around in them, and the electric field essentially amounts to an electric force. So that force allows those electrons to scatter or rearrange themselves in whatever way necessary to cancel out that force. The implications for light waves, which are waves in the electromagnetic field, is that light waves must vanish. The electric field, the field strength of the wave itself must vanish on a conducting surface. And so we can use this fact to build a container with which to house electromagnetic energy or light waves in and have them behave in a relatively predictable way.
Consider the inside of a hollow metal cube which has sides of length L, like an oven. Since all electric fields must vanish on the edges of the cube, or the inside walls of the oven, the longest wavelength allowed inside the box is lambda equals 2 times that length, L. Why twice L? Because half of a sine wave corresponds to the lowest possible mode, just a little single hump. Sine of n times pi, where n is any integer, is 0 after all. For such an electromagnetic wave, the electric field will look something like the amplitude times sine of pi x over L for this lowest possible mode. In general, such an electromagnetic wave will have components in all three spatial directions, as well as time, x, y, z, and t, and we can save those details for a course on electromagnetism. For now, the symmetry of the box allows us to focus on what's most important. That is, that this lowest possible electric field represents the lowest possible frequency of standing wave of light, if you like, that's allowed inside the oven. But of course, we can include many more. In principle, infinitely many more. We can parameterize the electric fields of the individual modes, say like En, with an amplitude An times sine of n pi x over L, where n is a strictly positive whole number. This corresponds to higher frequency modes of the electromagnetic field inside the oven, which are also allowed by the shape of the box because they also vanish on the edges. In other words, the allowed wavelengths of electromagnetic energy inside the oven are given with a wavelength of lambda equals 2L over n, where n, again, is an integer, 1, 2, 3, 4, etc.
This is an important observation that will pay dividends later on in the course, and that is that the spectrum of allowed wavelengths, the spectrum of allowed frequencies, is determined by the shape, the geometry of the container that they're in. So this gives us a sense in which the electromagnetic field is quantized inside the box, but this is not a quantum mechanics notion of quantization. This discretization of the electromagnetic field, this choice of specific wavelengths of light that are allowed inside this box, is purely a classical concept. It's purely from the geometry of the box. So now we come to kind of a natural question that occurred to physicists at the turn of the 20th century. So given that we can excite electromagnetic waves, standing waves, inside an oven like this, if we were to give that oven some fixed amount of energy, say E, and we open the oven door and look inside, what would we see? What colors of light, in other words, would come out? What is the distribution of electromagnetic waves? To figure this problem out, we need to start thinking about the energies of the electromagnetic standing waves inside the box. Before quantum mechanics, our understanding of energy in the electromagnetic field was that it was proportional to the square of the electric field plus the square of the magnetic field. It was the field strength of that field squared. In other words, for light waves, the energy of a light wave was understood to be proportional to the intensity of the light.
More precisely, the energy inside the box was given by E is equal to 1 over a constant, epsilon naught, times amplitude squared times the volume of the box. Since the electric field is a vector quantity, all the different modes of all the different electric field components, if you like, add together linearly. We also know that the light comes with discrete wavelengths parametrized by n. They must all be standing waves inside the oven, so we can sum over all the different amplitudes of all the different modes of the electromagnetic field to get the grand total energy, which is something like L cubed over epsilon naught times the sum from 1 to infinity of the amplitude of each of those individual modes a sub n squared. In other words, the energy of the light waves should be distributed amongst the amplitudes for the different modes an of the electromagnetic field.
And this doesn't solve our problem, it merely changes the question slightly. And now our question asks, if we impart an energy E into the oven, we know that that energy is going to be distributed amongst various amplitudes of the various modes of the electromagnetic wave. How is that energy distributed amongst the different amplitudes of the different modes? Here's the fundamental problem that was facing those physicists at the turn of the 20th century. Because the energy contributions from different colors didn't really depend on the color, there was no a priori way to determine what the distribution of energy should have been. It could be anything. It could be totally random. There was no guiding principle that specified how energy should be distributed amongst the electromagnetic field, or at least no first principles one. The equations of classical electrodynamics made a lot of sense, physically speaking, but trying to bring them into the fold of kind of modern understanding of, say, thermodynamics proved to be quite challenging. While it is true that if you put energy into a metal box, that energy will be dispersed amongst different modes of the electromagnetic field, the classical theory of electrodynamics does not give us a prescription for how that energy should be distributed amongst the different discrete modes of the electromagnetic field. Giving our oven a total energy E, we do not know how to distribute that E amongst all of those different modes. Without any natural prescription for it, the only option left to physicists was essentially the agnostic one. That is, all energy should be distributed amongst all modes evenly, or at least with equal probability. Right away, we run into some trouble, and that trouble has to do with infinity. You see, if, as classical electrodynamics predicts, the energy of every single mode of the electromagnetic field in the oven is essentially the same if it only depends on the amplitude of that mode, then the energy of a very high frequency mode is the same as a very low frequency mode. And so if we're distributing the energy equally amongst all the modes, we're going to end up distributing most of that energy amongst the modes with the highest values of n. Why? Because we have an infinite tower of modes where n keeps growing from 100 to 1,000, 10,000, a million, 10 million, a billion. Now, for our mathematically sophisticated viewers, no doubt you are concerned that such a process is not well defined. And in fact, that is precisely the problem. With an infinite set of things that you can distribute a finite amount of energy to, what does that even mean? Well, in practice, from a physicist's perspective, what it means is all of the energy that would be practical for us to consider would be distributed amongst modes with such high n that they would be beyond the visible spectrum of light. So beyond red at 700 nanometers, beyond blue at 450 nanometers, beyond violet at 400 nanometers, way beyond, into the ultraviolet. That is to say, all of those modes that are beyond the spectrum of visible light. Of course, nobody at that time believed that this theoretical prediction was true because it was in direct conflict with experimental observations. It's in direct conflict with human experience. If you heat up a piece of metal and watch it glow, it'll start to go from colorless to dull red to orange to yellow until it eventually starts to burn brighter and brighter and brighter. The same thing is true with your stovetop. The same thing is true with ovens that people built explicitly for this purpose. This paradox, this discrepancy between the theoretical calculations of what we thought we understood about electromagnetism and the blatant experiments, the blatant human experience of light emitted by thermal radiation, was labeled the ultraviolet catastrophe. And as we'll now see, the imposition of photons resolved the ultraviolet catastrophe in a very simple and clean way. The paradox of the ultraviolet catastrophe was resolved with the realization that light waves are quantized into photons, and those photons have energy that depends on the wavelength. Let's let little e sub n equal the energy of a photon of a wavelength of light, lambda n, from inside the box. So in other words, little en is equal to nhc over 2l. This slightly reframes our problem of distributing the total amount of energy by distributing it amongst an integral number of photons of wavelength lambda n. That is, we can rewrite our sum of the total energy as a sum over little n from 1 to infinity of n sub n times little e sub n, where now n sub n counts the number of photons of wavelength lambda n. In this form, we immediately notice two things. First, there must exist some maximum energy photon that's allowed in the oven when it has a total energy E. That is to say, the energy provides a finite cutoff, a minimum possible wavelength that can be supported with that much energy. So what's nice about this is it immediately reduces our infinite sum, our infinite distribution over all possible modes to a finite sum. In other words, we only need to partition the total energy of the oven into amongst a finite number of photon mode, those n sub n, for n less than n max. The second thing that we can observe, as we add more energy to the oven, that value of n max grows with that energy that we include. So ostensibly, the light waves, the photons that we could see when we open the oven door, the colors of that light will have smaller and smaller wavelengths, which is consistent with what we observe by heating some metal things up, by heating the oven up. It's consistent, in other words, with observation. So the fact that the individual photon energies vary with wavelength, the fact that it costs more energy to produce a photon of higher frequency, of smaller wavelength, means that when we distribute the energy over the different photons, we are more likely to give some energy to photons that cost less energy. More expensive photons will be present less often. And if you chase all the details and you do all the math correctly, which we will get to eventually in this course, you end up with a prediction for the number of photons of each individual wavelength color that you can see for a given energy given to the oven. And that prediction matches with experiment perfectly. If you're curious, the number of photons in an oven at a given temperature T can be written down. This is the famous Planck distribution. At this point, the little constant k can be thought of as just a convenient number that we use to multiply by a temperature and get an energy out. So we can translate the concept of temperature to the concept of energy. Same basic principle. So while it's true that quantum mechanics deals with microscopic things like atoms, like the particles that make up the atoms and things to that effect, we still need quantum mechanics to be able to describe how electromagnetic radiation, that is light, behaves in a classical or thermal setting. Thanks very much for watching. See you next time.